continue with chapter 11. And so, as far as the quantum theory goes, how was quantum theory developed? Quantum theory was developed from unusual light patterns. And so the unusual light pattern was for the H lamp, the hydrogen lamp. And so what was expected was a continuous spectrum. The spectrum is going to look like this. It's going to have, this would be the intensity of light. And then if we look at the colors, if we do this based on lambda, which is wavelength, then it's going to go reverse order. Roy, orange, with red is the longest wavelength. Roy G bid. And so the intensity of the light, we didn't get that much UV. UV's here, and infrared's here. UV and infrared, these are invisible. But what was expected was a continuous spectrum, that is, all colors would show some intensity. So this is continuous. But some people would not have recognized that this was unusual. What was unusual about the light pattern that they saw from the hydrogen lamp? And would you have recognized that this is unusual? And so what was observed is when we look at the intensity versus wavelength, we just see a red line here, a green line, blue line, and a violet line. This is a discontinuous spectrum. Or a line spectrum. And so some people will go, well, that's nothing unusual, but other people will go, yes, this is very unusual. This is very unusual because there's nothing here. Just blank. Nothing. Black. Black in the sense that no color. Well, I shouldn't say black. Black would mean it's just blank. And so this is the same thing. For example, the discovery of penicillin. Penicillin would have never been discovered had it not been for somebody recognizing that something unusual occurred. Do you know the story of Fleming's discovery of penicillin? Right, there are a whole bunch of cultures, I think bacteria cultures, that he left over the weekend. And when he came back, what was he expecting? He was expecting bacteria growth, right? What did he observe? He observed dead bacteria. And so how did the bacteria die? Normally if you cleaned it. And so some people might have just cleaned it and thought nothing of it. But he recognized it was unusual. And so it turns out some spores, I think fungal spores, landed on the bacteria and killed them. Right? Well, the same thing here. If you build an H lamp, you might not know, okay, this is unusual. What is unusual about a discontinuous or line spectrum? What is unusual about this is this. What is unusual is a continuous spectrum should be generated by exciting the electron. Can the electron go any speed it wants to go? Can you excite it to any energy? By giving it a little push, yeah. The harder the push, the faster the speed. And so the electron should not be restrained. So for example, if the electron wants to go 25 miles an hour, it's fine. If it wants to go 25.1 miles an hour, that's fine too. Just a little bit more energy, right? And so this is the reason why continuous spectrums was expected, because if it's red, this is actually energy. Remember, wavelength increases this way, energy increases the opposite way. And so here, what's observed is, okay, if it starts off this energy and gets a little bit more energetic, a little bit more energetic, a little bit more energetic, pretty soon, if you excite the electrons enough, you'll start emitting not red light, not orange light, not orange-yellow light, you'd start emitting white light. Right? So just keep exciting the electrons until you emit the whole rainbow of colors, because you got a lot of electrons, and so some of the electrons will be lower, some of them will be higher. You'll get the full rainbow. That's how light bulbs work. You know, the old-fashioned style light bulbs work. And so hydrogen has electron, however, it doesn't give the rainbow of colors. And so this was what was unusual. Why don't we see the rainbow of colors here? And so what do we have? Well, we had a pattern. And so normally when we have a pattern, then we do what? We try to see if there's maybe a mathematical equation that fits this. And so we got this pattern. And then, you know, this mathematical equation is called an empirical equation. What was empirical again? Empirical means that it's based on theory or based on experimental observations. Experimental law. This empirical equation we call Rydberg's law. So the Rydberg law or Rydberg equation just defines this mathematically, this pattern. And so, okay, we got a pattern. We could fit it with some kind of mathematical equation. The mathematical equation is pretty simple. You know, the energy is just equal to some constant times 1 over n, we call n final squared minus 1 over n initial squared, where n is an integer. You know, n equals 1, 2, 3, dot, dot, dot. A non-zero integer. And that's a mathematical equation. Okay, then what do we do? This, you know, then we come up with a, what's a scientific method after you come up with the law then, or some kind of regular kind of hypothesis? Could you have hypothesized, you know, would you have hypothesized this? Would you have hypothesized that the hydrogen lamp is going to give you an unusual light pattern? Would you have hypothesized that? Although a lot of people, you know, when I ask about the scientific method, a lot of people say that the scientific method starts off with a hypothesis, but I don't understand how. You know, even some scientists say if you start off with a hypothesis, you could end up biasing your results, because you might be looking for things that just only prove your hypothesis. And so, what's a hypothesis? The hypothesis is this. The hypothesis is that there are forbidden and allowed energies. In other words, energy is not continuous. Energy is not continuous. For an electron in an atom. Energy is not continuous for an electron in an atom. It is discontinuous. When it's discontinuous, we call it quantized. It is quantized. Quantized means it's discontinuous. And so, the hypothesis is this. We're not allowed any energy we want. And so this would be continuous. You can have any gravitational energy you want, depending on how high you want to go. So any height is allowed. Gravitational potential energy depends on mgh. H is the height. This person can go to higher energy or lower energy or anything in between. This would be quantized here. The energy occurs as discrete levels. And you can't have anything between. These are called forbidden energy. So any energy between these two are forbidden. It could be at this energy. So that would be quantized. This is for an electron and atom. Electrons in the sun make a continuous spectrum. Electrons in the sun. Electron in the sun. Do you get the full rainbow of colors from the sun? Yeah. But when you put an electron in an atom, then it behaves differently. And so electron in an atom is,
what is the difference?
Well, in the sun, the electrons, a sun consists of a plasma. A plasma is an ionized gas. And so you got a lot of ions there, and you have what we call free electrons. And the free electrons are free to move around anywhere in the sun's plasma. And so it's huge. The plasma is huge. Well, what happens is if you start shrinking down, pretty soon, if an electron is an atom, is it free to move anywhere it wants? Not really. It's kind of restricted to the confines of the atom. If the electrons are restricted to the confines of the atom, then it behaves, at least it doesn't really behave differently. You just don't notice it, the behavior, until you confine the electron to an atom. And so this is why a lot of people say quantum physics applies to really small. Have you ever heard that? Quantum physics, when we get really small particles, then it really becomes apparent. Quantum physics has always been around. Where does quantum physics come from? That's this hypothesis. This hypothesis led to a model. The first theory that came about from this is that Bohr proposed that the electron in the atom cannot have any energy it wants. It's going to have quantized energies or quantized energy levels that are going to look like this. And so Bohr theory, the electrons form orbits. And these orbits have very specific energy. And so the first orbit is called the n=1 orbit. The n=1 orbit is like this. There's no 0.5 orbit. There's no 0.2 orbit. The first orbit's n=1. The second orbit would be n=2. Okay, but there's nothing in between. So all the orbits in between n=1 and n=2 are forbidden. They're forbidden. This is forbidden. So it can't go less than 1. It's forbidden. And so n=1 is allowed, n=2 is allowed. What's the next one that's allowed? n=3. And so we have these orbits here, like this, that are allowed. And so this is what Bohr proposed. He proposed that, the electron can't orbit anywhere, it just has to orbit like this. These steps, though, aren't evenly sized steps. And so what does it look like? It looks like this, kind of. They aren't even because if you look at the this, it kind of looks even here, but it's not. The first orbit for the hydrogen atom is at 0.5 angstroms. The second orbit's about 2 angstroms. The third orbit's about 5 angstroms. The fourth orbit's getting closer to 9 angstroms. These are the energies associated with those orbits. So you can use, depending on the distance here, you can calculate the energies using physics, just regular physics. And so you can use regular physics to do this. The only thing is regular physics would predict any orbits allowed. And so this is the new quantum physics. The quantum physics predicts not any orbit is allowed. And then you might ask, okay, why is not any orbit allowed? Why is not any orbit allowed? And so what Bohr, you know what a postulate is? It's just taken without proof. Why isn't the 1.5 orbit not allowed? And the answer is because it's not allowed. That's it. That's what's observed. You know? And so science is just describing it, describing nature, and therefore that's a description. But of course we'd like a better description than that, because you know, it's like, why can you only drive 25 miles an hour and 35 miles an hour but not 30 miles an hour? Why is that forbidden? It's forbidden. It's impossible. Does it make any sense? It doesn't make any sense, because the electron is just a particle. And that particle should move any speed it wants to, depending on how much kinetic energy is around. So it doesn't make any sense at all. But it's okay, because this is what's observed. And so if this is what's observed, this is what's observed. Although this picture might not be correct. And in fact, this picture turned out to be wrong. Bohr theory turned out to be wrong. But Bohr theory, you know, it was promising. It was promising because what happens is, what Bohr proposed is these lines, these discrete lines in the line spectrum are a result of transitions between these steps. So for example, if an electron gets promoted to the 3rd floor, it's not going to stay there forever because that's high energy. Eventually it's going to drop back down. It could drop back down to the 2nd floor, or it could drop back down to the 1st floor. If it drops back down to the 2nd floor, then it emits the red light. And if we have an electron in the 4th floor, and it drops all the way back down to the 2nd floor, that's the green light that's observed. And then if we have an electron in the 5th floor, and it drops all the way back down to the 2nd floor, that's the blue. And then if we have an electron in the 6th orbit, an electron in the 6th orbit dropping down to the 2nd orbit, that would be the violet. And then if we have an electron in the 7th, so if we put an electron in the 7th orbit and drop that electron all the way back down to the 2nd, you know what that would be? Ultraviolet. So it's predicted there should be ultraviolet lines which are invisible. It was predicted. And so that was one of the successes of the Bohr theory. The Bohr theory predicted ultraviolet lines. They were observed. People detected them. Likewise, there should be infrared lines too. If the drop is smaller, then there should be infrared. Like for example, if we go from the 4th floor to the 3rd floor, that's infrared. Because the floors aren't evenly spaced. And so this is the result of this. And so when we see these lines, what we're seeing here are electrons. The reason why we don't see the whole rainbow of colors is because not every energy of orbit is allowed. And so this red line is due to the 3rd to 2nd floor. The green line is due to the 4th to the 2nd, 5th to the 2nd, 6th to the 2nd. And then past violet, there are ultraviolet lines. And in front of red, there are infrared lines that are observed as well. Okay, the reason why the Bohr model turned out to be wrong is because hydrogen is the simplest. What if we tried to make a lamp out of something a little bit more complicated, like helium. If we try to make a lamp out of helium, do you know what happens? It fails. And any other atom with more electrons than hydrogen. Hydrogen will only one electron, but any other atom with more than one electron, it fails. And so Bohr model was unable to explain anything with more than one electron, or describe anything with more than one electron. So anything, well, I shouldn't say any atom or any species, doesn't have to be an atom, it could be an ion, any species with more than one electron it fails. It meaning the Bohr model fails. And so if something like this fails, then what do we need? We need more hypotheses, or we need more observations? You've got to take more observations and see what's going on. And some of these observations led to some further development. And so Bohr was abandoned. This whole idea of orbits, although it's a nice picture, was abandoned. Not everything was abandoned by Bohr. You know, quantized energy levels retained. But some additional observations came about to help. The additional observations were one, the wave particle duality. So light waves have particle-like properties. And we call these photons. So for example, when we think about the difference between gamma radiation and radio waves, gamma is dangerous, or what was that?
High frequency.
High frequency. High frequency is high energy, right? High frequency is high energy. And so this actually won Einstein the Nobel Prize. We can, we can talk about energy of light. So what would you rather be hit with? Would you rather be hit with a pound of feathers or a pound of gold? Well, some people will say, it doesn't make a difference. They're the same thing, right? They're the same thing. Or what would you rather be hit with? A ton of feathers or a ton of gold? Some people will say, hey, it doesn't make any difference. Both of them are a ton, right? But you know what I'd rather be hit with? A ton of feathers, right? A ton of feathers, because each feather is not going to cause not much damage, right? And so it's the same thing as this. If somebody dropped, let's say, a pound of feathers off the top of the Empire State Building, and another person dropped a pound of lead off the top of the entire Empire State Building, is there any difference? Yeah, there's going to be a big difference, right, in what it hits. And so that's the whole idea about light, light photons. For example, if I had a 100-watt light bulb, and the 100-watt light bulb was emitting visible light, or a 100-watt light bulb emitting X-rays. And you might go, hey, it's 100 watts. 100 watts is 100 watts. It doesn't make any difference. You know what a watt is? watt is a joule of energy per second. So that's 100 joules of energy per second. And so I could have 100 joules of visible light hitting me in 1 second, or 100 joules of X-rays hitting me in 1 second. What would you rather be hit with? You'd rather be hit with visible light. You'd rather be hit with visible light, and the difference is because the photons of light pack a punch. And so we have to think of the photons. You just have fewer photons. You have fewer photons, but each photon packs more punch. You know, so it's like a pound of feathers versus a pound of lead. You have a lot more feathers, and each feather doesn't pack much punch. And so that would be like low energy light. The lead, you just have a small piece, but that would pack a lot of punch. Does that make sense? And so the way to think about this is this. You have let's say you have a gun, and you shoot a lead bullet into a crowd, let's say, this is an analogy that some people use. You shoot a lead bullet into a crowd, versus if you have the same gun and that shoot like little ping pong balls with the same energy, you know, what would cause more damage? Yeah, a lead bullet. And so this is the same thing with the photons. The photons is like this.
Heavier.
Right.
Element.
Gamma rays have photons that pack a lot of punch. Whereas radio waves have photons that don't pack much punch. Low energy. And so this is like, if you're working in a dark room, do you want to use a regular light bulb, or do you want to use a red light? Have you ever seen those dark rooms? No? All right. You have to be careful about this because there was, you know, there are some people who talk about radiation exposure. And when they talk about radiation exposure, they talk about, you know, how much radiation you're exposed to per kilogram of body mass. But when radiation is exposed, you know, does it distribute itself? Does all that energy distribute itself evenly over the entire body, or does it impact certain cells severely? It impacts certain cells severely. And so, you know, it depends on, it's been politicized, but it depends on who or how you want to talk about it. But anyway, this photon. It turns out that matter has wave properties. The wave properties of an electron are not noticeable. Until it is confined to a very small volume. And so when we look at a light bulb like this, the electron is pretty much free to move over this is tungsten metal. The electron is pretty much free to move over that entire metal filament because the electrons in metals are very loosely held. And so the electron, you know, this is why metals conduct electricity. So if we look at an electron in the sun, an electron in the sun is over a wide range. But what happens is if you confine it to a smaller and smaller range, then you start to notice things. This is like a fish. You know, a fish in the ocean, can it swim any speed it wants? A fish in the ocean swim any speed? Well, I mean, from 0 to whatever its max is it free? But if you start confining it to a smaller and smaller volume, is it as free? No, it's going to be constrained. For example, it can swim to one end, then has to flip around and swim to the other end, you know, and so it's going to be constrained. And so that's exactly what happens here. If we take an electron, this electron is free, you know, because the atoms are small. The tungsten filament's huge. So these electrons can move any speed at once, right? But when you start taking that, this is tungsten metal. And so this is macroscopic here. But if we go to a tungsten atom, this will be the nucleus here. Then all of a sudden, that fish, you know, is going to be constrained to a very, very small aquarium. And when it is constrained to a very, very small aquarium, then the wave properties make a difference. And so now this electron is not so free. And when we think about wave properties, it's like this. Here, we didn't notice these wave properties because when you're dealing with macroscopic things, this is the wavelength of matter. The wavelength is very small. And so if the wavelength is very small, if we want a little bit higher energy, then we have just a little bit shorter wavelength. And so let's say there's 1 billion wavelengths in here, you know, peak to peaks. If we go to 1 billion and 1, is there much difference between having a billion and a billion and 1? It's negligible. And so the energy difference between having 1 billion waves in there and 1 billion 1 waves is not even noticeable, right? It's so close. And then 1 billion and 2, and then 1 billion and 3, etc. But if we have, let's say we have 1/2 wavelength in here, this is for like a standing wave, then that's okay. But the next allowed one is going to be 1 full wave in here. We'll put 1 full wave. And then the next allowed one here will be 1.5 waves. And it turns out there's a significant energy difference between having a half a wave in here, a full wave, and 1.5 waves in here. Pretty big difference. Whereas there's very little difference between having 1 billion waves and 1 billion and 1 waves. Nothing. And so what we see here is energy is quantized by half wavelengths, actually, here, when we're looking at matter waves. And so this is 1/2 lambda. And so we can have 1/1/2 wavelength, we can have 2 1/2 wavelengths, we can have 3 1/2 wavelengths. Can we have, let's say, a quarter? It turns out we can't have a quarter. We got to fit everything in this tiny space. And so this is called n times 1/2 lambda, where n is equal to 1, 2, 3, etc. It's an integer. When we start getting to here, this is n equals, well, let's say 1 billion half wavelengths. Versus the next level that's allowed will be 1 billion and 1 half wavelengths. Then we don't notice it. So this appears to be continuous. And so this is why a tungsten light bulb can absorb pretty much any energy it wants. It could absorb infrared, it could absorb red, orange, yellow, green, blue, indigo, violet, and emit that because it's pretty much got energy levels all the way through here. And they're all tightly spaced because the energy difference is so small. And so even in a tungsten filament like this, energy is quantized, but you don't notice it. It's only when you make it an extremely small volume, the size of an atom, that you notice it.
So when we confine an electron to a tungsten atom, we have to worry about how many half wavelengths we can fit in here, otherwise
There's something called constructive interference and destructive interference of waves. Have you ever heard of that? So what happens is, if you take two waves and you match the peaks, so the peak matches the peak and the trough matches the trough, that's called constructive interference. But if you take two waves and you take the peak of one wave and the trough of another wave, you know what happens? It cancels each other out. It cancels, and so we call that forbidden. And so this is all part of this. And so it turns out when we have an electron in an atom, it has to be confined in the same way over here by half wavelengths. And so we're going to see forbidden energies and allowed energies in terms of the orbit. So this makes more sense. And then two, the other thing we have to worry about is something called the Heisenberg uncertainty principle. Another thing about the electron is this. You can only, if we pinpoint the energy of an electron, if we pinpoint energy of electron, then we cannot precisely determine position. In other words, we talk probabilities. This leads to probabilities. Electron is kind of like a bird. In a way. And so here's the bird nest analogy. Let's say the nest of the bird is here. And let's say the bird has so much energy. Let's say has so much, it can be here. Can you pinpoint where the bird is going to be next? No, but we have a probability because the bird only has a certain amount of energy, so the probability is it's going to be close to the nest. It's a low energy. And so it might be here, it might be here, it might be here, it might be here, it might be here. And so if we track the bird and just pinpoint its position once in a while, we can't really predict how it's flying or where it's going next. But what we're going to do is we're going to generate a probability map. Like this. And once in a while it might be out here, but it's kind of rare because it doesn't have that much energy. And so most of the time it's going to be here. And so this is going to be a called a probability distribution or probability distribution. Or electron cloud. And so what we just say is electron should be within the cloud somewhere with a certain amount of probability. You know, we can kind of isolate it because, you know, it can be infinitely far away, but we try to isolate it with a boundary. Like 95% of the time, it's going to stay within this boundary. And so we'll have a boundary like this, and we'll call it the 95% boundary. 95% of the time, the electron spends its time here, and then 5% it ventures outside the boundary. That would begin. And so with these two additional things, and with Bohr, we come up with the modern day theory of chemistry, which we call quantum mechanics. Well, quantum mechanics has been successful here. quantum mechanics can describe these lines in detail, the origin of these lines in the hydrogen lamp, which is different. Origin. The description's different, the results are the same. The equation, it turns out that the equation, from quantum mechanics, you still get the Rydberg equation. You get the exact same equation that Bohr used, except the description of what's happening is different. And so, quantum modern day theory of chemistry, we deal with orbitals, not orbits, as Bohr. And so with quantum mechanics, then we have no problem with helium lamps, mercury lamps, neon lamps. All right, so here's the Bohr model, but the Bohr model just kind of worked for the hydrogen, but it didn't work for anything else, so we abandoned it. The Bohr. Quantum jump, these are called transitions. Ground state is, when the electrons are on the lowest. Excited states are, third floor, whatever. Ground state for hydrogen atoms is the first floor. That's the lowest energy possible for a hydrogen atom. The excited electrons, photons are released, photons are absorbed. So this is another way of representing it. These are the quantized energy levels here. And like I said, the steps aren't even. The steps are uneven here. This comes the gaps. So here, electrons in the ground state here, the first orbit or the first floor, and it gets excited. There are different ways you can excite the electron. You could heat it up, kinetic energy. You could pass electricity through it. You could shine light on it, but you promote the electron up here. The electron doesn't stay excited forever. Eventually it's going to drop. In this case it drops here and it's a UV photon. From the second to the first floor. The energy increase, 984 kilojoules per mole, is the same as the energy that's released. So, contributions of the Bohr model, we have the principal energy and what we call the principal quantum numbers. N is the quantum number, N equals 1, 2, 3, etc. We call the principal quantum numbers. But Bohr was abandoned and replaced by the quantum mechanical model of the atoms. We'll spend more time on this. Quantum mechanical model of the atom, atomic concept that recognizes 4 quantum numbers by way to electron energy. Now, okay, this, there's a lot of jumping around here because of the book, of course. But basically, quantum mechanics has something. Quantum mechanics is going to describe the electron fully, or as fully as you can. When we describe the electron, what do we want to know? We want to know its energy and position. And we call that like structure. Electron structure. And what's happening with the electron? And that turns out to be critical for chemical properties and whatnot. And so from quantum mechanics, we get the equation of quantum mechanics. The equation of quantum mechanics is called the Schrödinger equation. Schrödinger equation. What the Schrödinger equation is going to do is it's going to tell us about the energy and it's going to tell us about the position of the electron. And so this is going to tell us about, I should say, the allowed energies.
allowed energy, position. We aren't going to do the math. We're going to skip the math of the Schrodinger equation. What we're going to do is we're going to just kind of get a semi-mathematical. We're going to skip the bulk of the math, but we're going to retain some features. The allowed energy and position of the electron, this is called an orbital. We're going to skip the math and determine what orbitals are allowed. Based on a mathematical pattern. And what they look like. In terms of probability distribution. The probability distribution we call electron cloud. It turns out there are 4 variables in the Schrodinger equation. The answer is turns out there are an infinite number of answers to the Schrodinger equation. The answer to the Schrodinger equation for an atom there are an infinite number of allowed orbitals. But there are also an infinite number of forbidden orbitals. And so what we want to do is we want to be able to figure out what is forbidden and what is allowed based on the Schrodinger equation. Do you want to memorize all infinite number of allowed? It's impossible. And so what we have to do is we have to look for patterns. The patterns turn out to be simple, mathematically simple. And so what we do is we look for patterns. Look for patterns. Otherwise, it's impossible. One of the patterns is this. There are 4 variables from the Schrodinger equation. Depends on N, L, M, and S. N, L, M, and S. Well, actually, let's just do N, L, and M first. N, L, and M. Sorry. N, L, and M. And so based on the mathematics of the Schrodinger equation, n can only equal 1, 2, 3, 4, all the way to infinity. And so all of a sudden we see that non-integer values are forbidden. Only integer values are allowed. So we can't have any fractional values. And so there are an infinite number of allowed and an infinite number of forbidden. And so these are how we figure out what's allowed. So these are allowed by the Schrodinger equation. Otherwise, it doesn't work.
So if you tried to plug in 1.1, it would fail. Schrodinger equation.
When we give this a name, we call this the principal quantum number. Principal quantum number.
Misspell. Yes, I did.
Principal. Principal quantum number. So this basically tells us the energy level. You know, so the higher the number, the greater the energy. And so typically we map it out vertically like this. So n equals 1 is going to be down lower. N equals infinity is going to be way up higher. And then we have L. L is going to take on all values from 0, 1, 2, 3, ... to a max of n minus 1. And so the maximum L value is going to be n minus 1. So we can do that over here. So for example, if we're looking at L here, if n equals 1, what's our...
0.
Yeah, 0. If n equals 2,
1.
then what are we allowed?
1.
We're allowed 0 and 1. If n equals 3, what are we allowed? We're allowed 0, 1, 2. If n equals 4, we're allowed 0, 1, 2, 3. We give names to the L values. An L equals 0 is called S. An L equals 1 is called a P. An L equals 2 is called a D. And then F. Then it goes alphabetical, F, G, H, I. And so this is an S. This is an S and a P. This is an S, P, and a D. This is S, P, D, and an F. Those are all allowed. So is a P allowed for n equals 1? For example, if we tried to do a P, is that allowed or is that forbidden? This is forbidden. Why? Because it violates the Schrodinger equation, which violates quantum mechanics. For each L, we will have a set of M's. A set of M's. For each L, we will have a set of M's. So the M is going to go from minus L, ... through 0, ... to plus L. So it's going to go from minus L to plus L, hitting all the integers. So we have to look at each L value first. And so when we go to M, then it's based on our L value. So if L equals 0, we're going to go from minus 0 to plus 0. Well, if L is equal to 0, then M is equal to 0. If L is equal to 1, then M is going to take the values from minus 1 to 0 to plus 1. If L is equal to 2, then what is M equal to? Negative 2, negative 1, 0, 1, 2. If L equals 3, then we have negative 3, negative 2, -1, 0, 1, 2, 3.
We have one more called S. I'm not going to talk about it right now. I'll talk about S a little bit later. So what we're going to do is we're going to build up something called an orbital energy level diagram.
Turns out the higher the L, the greater the energy. So I'm oversimplifying here, but orbital energy level diagram. The lowest energy is going to be n equals 1. And if n equals 1, then L is equal to 0. And we draw a line here. M is equal to
-1, 0.
no, M goes from negative L to positive L. So M is equal to 0. And so this orbital here, we give the designation of 1, 0, 0. This is NLM. And what we call this is, we call this the 1s orbital. Because n is equal to 1, L is equal to 0. L equals 0 is an S, so this is called a 1s orbital. That's allowed. What's the next allowed orbital? It's n equals 2. N equals 2 is higher in energy. When n equals 2, then we have two possible L values. L can equal 0. If L is equal to 0, then M is equal to 0. And so we call this a 2, 0, 0 orbital, or a 2s orbital. 2s orbital. Now, if L equals 1, it turns out L equals 1 is slightly higher in energy. Not significantly, but we have 3 M values. And so let me write the M values up here. We're going to have M minus 1. And so N is 2, L is 1, M is minus 1. We get the 1, 1, minus 1 orbital. The 1, 1, minus 1 orbital is called a 2p orbital. And then M can equal 0. This would be the 1, 1, 0 orbital. This is another 2p orbital. And then we're going to have M equals plus 1. And this will be a 1, 1, 1 orbital, which is also a 2p orbital. And so we end up with 3 2p orbitals. The difference is the M value here. But the M value is not part of this designation, so all three are the same 2p orbital. All right, let's take a break here and then we'll continue. Go on.